Hello everyone, this is the solution video to Lab Exam 3. Now in this exam we had a function to code, pDelay, and it accepted magnitude, phase, and omega, which are basically the body vectors. And then we have also an overshoot value, the desired overshoot value, and the task is the following. We are going to use these vectors in order to design a p-type controller using the body method here for the system that has this magnitude and this phase basically. But that's not only it. The second part of this task is to assume that there will be a 2-second delay that will be added to the system, and then we will still use the minimum phase acquired magnitude and phase vectors in order to design the p-type controller for this delayed system. So K is basically for the non-delay part, and KD is basically the p-type controller that is designed for GS times e to the power of minus 2s, basically the delayed part. For the same overshoot value, basically, as we go through, you'll see that it's not that hard. Basically, what we will do is we will only use these vectors, nothing else. No complicated functions, no toolboxes, etc. Just plain coding, and we'll acquire the controller for both of the systems, and we return them simultaneously. So that's basically the important part here. So before I dive into everything, let me also note or show you that we have a relation here between zeta and phi m. And if you've solved this task here or question, you could have just designed one part. If you don't know the other part, you should have defined KD equals 0 and then returned that, or K equals 0 and return that. So now I have two scripts basically. One will be the function that I'm going to code, and the other one is the test function here. So let's begin with the test function. Now, in order to test this thing, we need a transfer function, but before that, before I define anything about that, the vectors for the magnitude, the phase, and omega can be acquired by the body command. That is not the part of the function, so you will only need this, but you can code your script that accepts a transfer function and basically obtains the magnitude, phase, and omega. Now, as you might know or remember, we need to get rid of the unnecessary dimensions here, because if you call this, and I'm going to show it in a minute, then this assumes that it might be a multi-input, multi-output system. Therefore, it has multiple vectors in it. But since we are passing in a single input, single output system, there is just an extra dimension that we cannot use, basically. So we squeeze it into a smaller size if there's extra dimension. So phase. There we go. Now, since we have this data, let us also define a certain overshoot, 10% overshoot, for example. And basically, that's it. We will going to take this and design the controller, or controllers even. Now, let me also, by the way, test this by using feedback command. And we can use K for GS if we have designed that. And we can also have a delayed part, delayed, that uses KD, but there will be a transfer function, the delay part, let's say 2 seconds IO delay, then 2 seconds. That's basically the task. You should design a controller K. You should also design a controller KD that assumes this system instead of GS, and both should have 10% overshoot, ideally. So in order to check that, maybe we can use the step info, pass in that, maybe the delayed version 2, so TS delayed, and then we can check the overshoot value. Now, in terms of a transfer function, let's come up with one. Let's use, for example, such a transfer function. Now, of course, there was no example for you to use, but it's not about the function, the transfer function, or the vectors. It's more about the code, and you'll see in a minute what I mean by that. So now here's also a little note. The phase value for the obtained controllers are more important than the resulting overshoot values. Therefore, do not try to improve the closed loop overshoot value. By this, I mean, in order to be able to check this numerically, I wanted you to just leave it as it is. Now, you can check your lecture notes. When you design a controller, you design it and then check the overshoot, but I wanted you to leave it at that, because if you improve it a little bit, you'll get a different K value, or some of you wouldn't improve that much, so it would become hard to check everything numerically. So now basically we're done with this, so let me also maybe introduce something here, or maybe not here. We'll see. Now, in the delay function, so what is this function about? First of all, since we have an overshoot value, since we will use the phase margin, the first step is to use zeta, or define zeta. So minus log overshoot divided by the square root of pi squared plus log overshoot squared. Now, this is the first step, and then we have this relation here. So we'll code that part. Now here we have to be careful, let's call this phi m, because the inverse tangent and 2 times zeta divided by square root of minus 2 times zeta squared plus another square root 1 plus 4 times zeta to the power of 4. Now, it is important to remember that we have this phase vector, but if you remember the body plot, there is this phase plot that is in degrees. So here you have to be really careful, because if you use A10, it will be in radians. You can either multiply this with 180 and divide it by pi, this would be the conversion, or you can also use the A10D function, and you can see it returns the inverse tangent in degrees. A10 itself does not return it there as in degrees, it returns in radians. So it's rather important to remember that. So that was one of the pitfalls that you might fall in. So once we have that, the desired phase value that we want for our controller in order to achieve that overshoot value is, since it's the phase margin phi m, we have to add this much angle to the 180 marginal bound in order to obtain the overshoot, because at 180, at negative 180, we have basically zeta 0 and 100% overshoot, but we have a certain percentage in as the desired value. Therefore, we should go a little bit to the left, and that amount is phi m here. So let's add this phi m. Once we have that, the important thing here is the following. If you use the body function itself without any output arguments, you'll get a figure, and then you can right click and do stuff. But if we were to do this manually, what is the need here? What can we do here? If we check for exact phase d, that might not be able or that might not be available to us, because it's a numerical data and we use a logarithmic spacing strategy. Therefore, it might not be that easy to find it, and the exact point might not exist. So the best way approaching this would be to look at the difference between the phase and the desired phase value and its absolute value. Now, if you don't use the absolute value here, then this wouldn't work, because we have negative values. We subtract another negative value, it would be even smaller. So there's this kind of motion that we will see if we don't use the absolute value. The absolute value means that we care about the difference, and the difference should be minimum because yeah, phase should be phase D ideally. So we will use the minimum function here, and then of course we can get the value, but we don't really care about that. We only need the index here. So once we've done that, we can basically look for omega index. This would give us the omega value, and then we can use magval, the magnitude value that we might be interested in. We can also maybe obtain the phase value. Phase. And of course the controller here would be then k equals 1 divided by magval. Because k times g is equal to -1, therefore k times g, its absolute value should be equal to 1. And since we are dealing with positive coefficients, the k value that we are looking for is the inverse of the magnitudes at that point. So that's the first part. So we might just display it in order to see what's really going on here. Let's have a small info message here. Let's call it no delay. We don't have any delay. And then let's display the phase, the desired phase. That's the phase val. Of course, this part is not necessary. I'm just creating a info message here. This is the desired phase value that we were looking for. This is the actual phase. So string phase val. And then we will have the frequency where this happens. Omega val. And then maybe also the k value here. I guess this should be it. And if you're solving this problem just for the first part, you have to define kd equals 0 in order to return 0 instead of nothing. Because if you leave it like k, you'll get an error message because there is this protocol that we will call it with 2 outputs in order to check both of the coefficients individually. Therefore, you have to use it like that. So once we have that, let me just get rid of the delayed part. And let's check it out. I guess this should be it. Now, let's call the test function. And that's basically the solution to the first part. Now, of course, if I want to be a little bit more, if I want to increase the accuracy in this case, I know that this is even sufficient. I can also stop at 10 to the power of 1, but let me use just the whole vector here with a little bit more points in order to see an even closer result here. So that's basically a closer result in this case. Of course, since I will be the one who is generating this vector and testing it out, so this is basically my test script. This would be your script, and I would then look for k and kd. It's not a big deal for you, and that's also the reason why I didn't give any example for this solution here, because I'm going to test it. So it's really relying on this relation, the search algorithm, and then taking the value and then the inverse, of course. So that's the first part here. Let us look for the delayed part. Now, in this case, it is important to remember the fact that there is a slight difference if we add delay. Now, instead of looking at gs, we will be looking at -2s like this. And if we plug in j omega and examine this, you'll see that, first of all, if I take the magnitude of this, it's basically equal to their individual multiplication. And we know that this, if you write it in cosine and sine form, this has basically gain 1, so, or magnitude 1, so we're left with the same gain vector as before the delay. So the mag, if I am going to write it here, so mag delayed is basically magnitude. That doesn't change. Of course, omega does not change. So omega delayed is also omega. But the only change here is for phase delayed. So what can I do about this? Now, it is important to remember, in order to solve this, to remember that the argument of this and this is basically equal to the sum of the arguments of the individual terms. And here, this is basically already theta. So this is minus 2 omega. The argument of that is minus 2 omega. So argument, and then minus 2 omega. That's already, that should be already obvious because we have a j term here. This is basically a polar coordinate representation, therefore we can directly see that the argument should be 2 times omega. Of course, 2 comes from the fact that we have 2 seconds of delay. If that would change, this would change. Now, the problem here is again the following. As we should have been careful with the A10D here, we should be careful about this because this is in degrees. This phase vector is in degrees. But the omega value is in radians per second. So again, we need a little conversion, namely times 180 divided by pi. So basically, if I define a new phase delayed vector like this, assign it to phase minus 2 times omega times 180 divided by pi, I should basically get the delayed phase vector. So I know that the magnitude omega is the same. The only thing that changed is basically this vector. So ideally, you would code this function and then you would pass in the magnitude and phase of GS, design K, the magnitude and phase of the delayed version, and design KD. It's possible, but this is a task to kind of remind you that there's this relation and you don't really need the delayed body vectors in order to design the controller. If you know the minimum phase version without the delay, you can just work it yourself out. Now we have this relation, of course. Now let me just add this correction factor here. So, well, it's basically the same. But now the important part is to basically copy and paste this first stuff here, because we still look for the same. But now we have phase delayed instead of phase, and we look for the desired value for phase delayed. And then, of course, we have certain values here, but the only thing that I'm going to change is this phase vector here, and that should be basically KD. So let me also display this part here. So 2 seconds of delay, and then the phase is that, the phase val is basically that, the omega and the KD value in this case should be that. So I guess we should be good to go. Now let's come to our test script. Let's again enable these and let's test it out. Now this is basically again the desired value. This is it. Now you can observe that the omega value here is approximately 3 radians per second. But here we are close to a different value, like 0.24. Now, if I look at info, I can see that there is a 10% overshoot. To the first digit, it's basically correct for this first system. Now, if I look at info delayed, we have basically a 7.21% overshoot. Now, this was exactly the point where I didn't require you to update your overshoot value. And Actually, technically, if you are writing a code and you don't know what the magnitude and phase values are, or you don't know the system, it's not really easy to correct this. So if you try to add, for example, 10 degrees, it might work for some class of systems, but it might be even worse for other class of systems. So there's also not a real way to kind of implement that. You might maybe look for a plus 10 degrees and then see if it's improving, or minus 10 degrees. If that's improving, one of them would be improving, and you can maybe iterate through that, but that's not really the point of this task here. So yeah, that's basically it. There were some pitfalls. One of them is to convert this into degrees, and then here to remember that this should be in degrees too. If you are using 2 times omega, it would not be correct. This should have been converted into degrees. And then the search algorithm is here also important. It's a basic one, but still it is important. If you use phase equals phase d, that would not be a good idea because that might not exist. Therefore, you might end up in an empty value. And then basically, if you know to design a p-type controller for any mag phase vector or omega vector, then this would basically work. And you can also see that actually we don't really need omega here, but to be more general, I have just provided the input here. So you could change the overshoot value and see what's really going on here, but the basic structure of the code would be like this. So this was 50 points. If you achieve this here, that should be 50 points. And well, this is the other half of the solution, so 50 points for this. Yeah, that's it. Hope that this was helpful for you. See you in the next video.